diagonalize the matrix if possible. So we are given a matrix, also given that the eigenvalues of A are 1 and 2. So only two eigenvalues. It's a 3 by 3 matrix. So from one of these two eigenvalues must have a two-dimensional eigenspace. Then we'll have enough eigenvectors. So we need 3 eigenvectors from these two eigenvalues. So pretty much diagonalize means we want to find a diagonal matrix D of eigenvalues and an invertible matrix P whose columns are the corresponding eigenvectors. So find D and P such that A equals P D P inverse. Okay, so this is this type of factorization we are trying here, and the eigenvalues are given here, so it's a little bit of, saved a lot of work. Otherwise we would just solve determinant of A minus lambda I, or determinant of lambda I minus A equals 0. So solving this characteristic equation would give us the eigenvalues. That's what we have. Then to find the corresponding eigenvectors, now we just find the eigenspace. The eigenspace, or the null space of A minus lambda I x equals 0, or we just solve this equation, A minus lambda I x equals 0 for x. So here is A minus lambda I, so I just worked out here. I is a 3 by 3 identity matrix in this case, 0 0 like this, and lambda I, when we multiply by lambda, is going to be lambda here, so this, and we subtract. Now let's find the corresponding eigenvectors. Okay, so here for lambda equals 1, so we just use this. We got here A minus lambda I matrix x equals 0. So we solve this, and x here, because it's a 3 by 3 matrix, so we got a vector like this. Now we solve this, and I'm going to write just the augmented matrix. So A minus lambda I with I equals lambda equals 1, sorry, lambda equals 1. So lambda equals 1, so -1, -4, -6 equals 0. So here -1, negative lambda is 1, -3, and here is 1, 2, 5 minus 1, 4, 0. Okay, so we need to solve this now. First we change this into echelon form. We just convert into row echelon form. So 1 2 4, let's move this, and 1 minus 1 0, 1 minus 1 0. So R1 and R3, let's interchange R1 and R3. So 1 2 4 here. Now -1, -1, -3 0, -1, -4, -6 0. Okay, just interchange R1 and R3. Now we want to work on R2, so R2 plus R1, similarly R3 plus R1. So not doing anything on R1. -1 plus 1 0, -1 plus 2 is 1, 1, -1 0, -2, -2 0. So here is a pivot, here is pivot. Now we need to make this 0. Look at these two rows carefully. 1 1, oh, this is just -2 times this. If we multiply this by 2 and add with third row, it's going to be 0 0, because 2. So this one is same as 1 2 4 0 0 1 1 0. So multiply by 2 and add, we get 0 0 0 0. So this is in echelon form. Pivot, there is no pivot here, so this is x1, x2, x3, and it's free because there is no pivot. Okay, from the second row 1 x2 plus 1 x3 is 0, and x3 is just x3 because it's a free variable, or x2 equals, subtract x3 from both sides, and from the first row we get x1 plus 2x2 plus 4x3 equals 0, or subtract 2x2 and 4x3, we get x1 equals negative 2x2 minus 4x3, and x2 is in fact negative x3, so this is same as negative 2 times x2 is negative x3, so that's positive. So 2x3 minus 4x3, 2x3 minus 4x3 is just negative 2x3. So x2 is here and x1 is here, and x3 is just free variable. So thus we found the corresponding eigenvector for lambda equals 1, or a basis for the eigenspace. So thus x equals x1, x2, x3, which is x1 is negative 2x3, x2 is negative x3, x3 is just x3. In each we got x3, so we can pull out negative 2, negative 1, and here is 1. So we got an eigenvector. So let me put in that way. So thus for lambda equals 1, we have this eigenvector negative 1, negative 2, negative 1, 1. Okay, if you think there are a lot of negatives, we can multiply this vector by any non-zero number, still get eigenvector. So we could have multiplied by negative 1. That would make 2, 1, negative 1. So this is an eigenpair. Now we need to do the same work for lambda equals 2. Look, this is a 3 by 3. We needed 3 eigenvectors, linearly independent. We just have 1 now. So hopefully for lambda equals 2, we will get the eigenspace, two-dimensional eigenspace, or 2 eigenvectors, linearly independent. So let's do the same work. So I'm going to erase and just copy these lines. Okay. So lambda equals 2. Plug in lambda equals 2 here. So we are here. So let me swap row 1 and row 3 and row 1. So 1, 2, 3 on the top, then negative 1, negative 2, negative 3, and this one is negative 2, negative 4, negative 6 equals 0. Now let's work on R2, row 2 and row 3. So row 2, so row 1 is just this. Add R2 with R1, negative 1, 1, 0. If you look at it closely, row 2 is just negative 1 times row 1. So pretty much all 0. Multiply by 2 and add, we get all 0. So this is x1, x2, x3. So we got in reduced row echelon form. Only one pivot here. So x2 and x3 both free variables. Okay. Now from the first row, that's the only non-zero row. So we get 1x1 plus 2x2 plus 3x3 equals 0. Subtract 2x2 and 3x3. We get x1 equals negative 2x2 minus 3x3. Thus we got the corresponding eigenvector, which is x1, x2, x3. Okay, so this is from the previous one, negative 2, negative 1, 1. X1 is negative 2x2 minus 3x3. X2 is free, so just x2. X3 is free. Okay, now we need to work on this here. So that is this x equals, in fact, x2 and x3. There are two types of arbitrary numbers, so free variables. So x2 out, if I do that, from the first component negative 2, here is 1, there is no x2, so 0. So we get 1 basis vector for the eigenspace, plus here I can pull x3 out, that leaves negative 3, no x3, so 0 and 1. So I got 2. So from the previous eigenvalue 1, we got 1 eigenvector, but for lambda equals 2, for this lambda equals 2, I got 2 eigenvectors. So this is how we get 1, 2 and 3, and which is good. That's why we can diagonalize this 3 by 3 matrix. If we had only one eigenvector here, then this matrix would not be diagonalizable. Okay, so here for lambda equals 2, we got 2 eigenvectors. So let me put here. Okay, so thus the diagonal matrix is, so 2 and 1 are eigenvalues, so it doesn't matter which one you write first. 1 and 2 comes twice because we got 2 eigenvectors, 2, 2, all zeros. And P is the matrix of corresponding eigenvectors. So we started with 1, so we must write 1 in first column, so we must write the corresponding eigenvector here. For 1, negative 2, negative 1, 1. Or we could multiply this by any non-zero number. For 2, 2, there are 2 of them, so it doesn't matter which one you write first. So negative 2, 1, 0, negative 3, 0, 1. By the way, these 3 eigenvectors are linearly independent. So these columns are linearly independent. So P is invertible, the inverse exists. So thus our A is P inverse dP, where D and P are found there. As above. This factorization is called diagonalizing the matrix.